Can start. And welcome to this third soft discussion day. It's my pleasure to introduce the speakers. I am Eleonora Secchi from ETH Zurich, and I will present the event of today. As usual in the past events, we will have first the Ask Me Anything with Professor Piazza and Professor Sciortino for about 30 minutes, followed by the talk from Stefano Sacanna and a Q&A of 30 plus 15 minutes. The moderator for the Ask Me Anything is Professor Sofia Kantorovich, which is my pleasure to introduce. Sofia had a very across international border academic journey. She started with bachelor, master, and postdoctoral studies in the Ural Federal University in Russia, followed by a postdoc at the Max Planck Institute for Polymer Research in Mainz. Then she became Hubble Fellow at the Institute for Computational Physics in Stuttgart. Then, after becoming a senior researcher at the University of Rome La Sapienza, she joined the University of Vienna, where she became first associate professor and then since 2022 full professor. In the meantime, since 2011, she has also been associate professor in the Institute of Natural Science in the Ural Federal University in Russia. She gave a pivotal contribution in theory and simulation of dipolar soft matter. And in particular, the system of interest has been magnetic soft matter, including the use of magnetic nanoparticles to treat cancer, charged soft matter, and DNA duplexes and self-assembly, developing methods of statistical physics and computer simulation to better understand these systems. And then it's my pleasure to let her speak and introduce our speaker for the Ask Me Anything today.
Thank you very much, Eleonora. Hi, everybody. My pleasure to welcome you to this new third edition of IsoDays. And it's really a pleasure for me to moderate this session of Ask Me Anything. And let me introduce the two guests. So the two guests are Roberto Piazza and Francesco Sciortino. It's different to underestimate the contribution of both to soft metaphysics, rheology, self-assembly, and they have a very similar, in a way, almost synchronized series. So they both graduated in Italy and made their PhDs in Italy, then spent 2-year postdoc in the United States. I would not go into every detail because both CVs are online, and if you want to know really precise dates and precise places, you can, of course, look it up. And then they came back to Italy, and since then, really pursued the career in Italy. And from 2005, full professors. So Roberto is in Milan and Francesco is at the University of Rome La Sapienza. And actually, so to not postpone and not keep the introduction too long, I would like to, based on this CVs, actually directly go to my first question that I had since quite a while looking. So I got to know both Roberto and Francesco more than 10 years ago, and it was always a pleasure. But my question was always the following, and now it's even crystallized in something probably more round in a way. Both of you, after 2 years in the United States, went back to Italy. And I have a very clear question, why? So what was the main reason why both of you, after doing very successful postdoc abroad, went back and went on really focused career in Italy? Who wanna start?
The youngest. Francesco, you start.
Then Francesco starts, yes.
For me, it's very easy. It was a family decision. We really didn't want to. I mean, we're pretty happy in Boston together. I mean, far from any family constraint, nice life, young. Boston is a beautiful European city. Science is perfect there. You meet everybody you want to meet in that area. So Boston was great, but still the American way of living was not what we wanted to have for our kids. And so when we had the possibility to go back, in my case, to Sardinia, I had an offer to work there, and I accepted it. Marilena supported me, my wife supported me in this choice. She was more interested in me to go back there, I must say. Possibly I could have stayed in the state, but it was a shared family decision, let's put it this way.
Okay. And you, Roberto?
Concerning me, first of all, I have been in the States only for 1 year, not 2. Yes, it's just 1 year, 1 year. And the reason why I came back was basically because I wanted to marry my fiancée. I managed to keep her at bay for about 7 years, and after 7 years, I had to do something. And the decision was, I mean, one of the main decisions. But I agree with Francesco that there are many things that you have to balance, which is not only the fact that living in the States when you have young kids is not easy. Not at all, but there are also many other things. Of course, in the United States, you have an enormous amount of connections with other people doing research and science, great scientists, and you have seminars every day in your place. And that's, I mean, probably is the most important part of my experience in the States. At the same time, I think that this is valid also for Francesco. The kind of science we do is very particular. We like very much to be on the field by ourselves. Both me, which I still like to spend time in the lab as much as I can, and I'm sure, I mean, I know Francesco very well, and I know that also Francesco is a person that is on the computer by himself. And that's something that is easier in a place like Italy, where you are not going to get big spaces, a lot of PhDs and postdocs, which is a bad thing in terms of the amount of work you can perform. But in terms of, you have less danger of doing what, unfortunately, many young people are doing all over the world, which is when they are less than 40, 35 or something similar, they just put on their tie, or if they are women, they not without tie, and they stay in their office and they have the postdocs and the PhD doing everything. Both me and Francesco, we are not that way. We like to be doing physics directly still now, even if we are getting old. And I think that Italy, if you really struggle, might be a place where you can do it. Well, you can do it at least until you reach the point where you have too many other things. And of course, you need the help of several people around you. But still, being inside science and soft matter is a place where you have to be, much more than other traditional fields of physics, is an important point. That's my opinion.
Cool. You almost answered my second question that I wanted to ask, but before going directly to that, from both of you, from Francesco in a more explicit way, from you in a more subtle formulation, but I heard the American way of living is so much different from an Italian way of living. And you hear this phrase, like French way of living. But each of us, when we hear this phrase, we put something personal into this term. So, Francesco, what did you put when you call it, so the American way of living? Because a lot of kids are growing in the US, clearly, right? So, and they do survive. And they're fine as far as we're concerned. But what exactly was meant when you said that?
No, I mean, it's in Italy, you know, we are, especially in the south of Italy at that time, we had very strong family ties, right? Kids were used to grow with grandfather, grandmothers, and large family, big celebration, a lot of people, a lot of sharing. In the US, families are split in different cities, sometimes very far from, even from in kilometric point of view. I mean, not so close. And so only Thanksgiving and sometimes Christmas are the moments where the family has some reunion. Of course, we ended up in Rome, which is not Palermo, but at that time we didn't know. We were still hoping possibly to find at the end some position close to our families. I mean, the family life at that time was different. Now, also, my son is probably live things in a different way. My daughter, they are both out of Rome already, and they probably will stay there for a long time. We'll see. I mean, but we like to be close. And that's an important family tie that was not possible in the US.
Mm-hmm. And you, Roberto?
Well, I mean, I'm not saying that. I mean, I have to be very explicit. I think that all Europeans and Italians in particular should spend some time in the United States, because here we tend to live too much in a kind of cotton wool. You have friends, you have family, you have all this relation. When you spend some time in the States, you learn what it means to be on your own foot, on your feet. And that's an important experience. At the same time, well, depends on your conception of life. I think that science is not only my profession, it is a style of looking at the world, and that means also many other things together. And so doing science in that form in the European culture is sometimes easier than in the United States. Competition is good, but when it's excessive, it can be a disaster for people. And of course, it's easier to make good friendships with colleagues. And I think that me and Francesco we are, I think, a very good example of two people that started as two very different researchers doing different things. Sometime in competition, even in terms of position here in Italy, and we end up as friends. I think of Francesco as an important friend, and being able of having friends after the friends you get when you are a young person is something that happens if you take your profession, your job, as something more than just doing being a professional in science. It's like doing. I think that this is part of my life, and there are people with whom I share this thing. Of course, it means also people from the United States. I have several friends which are from the States, and when I meet them, they really, I feel not to be with colleagues, but also with friends. But there it's somehow difficult. And of course, then it depends on the time, the period of your life. Especially now, for sure, it's not a country for old men, and that's a real story. But that's a question of taste. But I think that the experience in the States, it's a good experience for everyone.
Okay, both of you also say so, like Francesco already mentioned his son, and you also say young people. So clearly the situation from, so what was that, 89, so late 80s, early 90s, changed dramatically in terms of cosmopolitization, of increasing mobility, and also the development of this online tools for positive or negative reasons that can be discussed. But still, now the world has changed. The world has really significantly changed since then. So, and had you had a chance now so imagine that this is now that you are graduating. So you are getting your diploma. So yesterday you got your diploma as PhD, and you both have offers in the US. The dream place of yours. You can choose now arbitrarily the place. What would you do now? Would you do the same? Would you recommend your kids to do the same? So that is like, there are two aspects, right? Would you, being now young, well, not that you are old, but at that stage of your career development, let's put it like that. Let's put it in a delicate way. But like in that stage of career, what would you do now? Would you follow the same path?
Probably yes. Well, I know. I could have also stayed in the state. I mean, you know, life it's a combination of random events. So I say we wanted to come back to Italy, but for example, without an offer from the Sardinia center where I went to work, I would have stayed in the state probably at the time. So yeah, I know that life and science, not only life, but science has changed a lot in the last 30, 40 years. There's been a lot of differences in the way we do science and in the way we perceive our career. And of course, the real problem again in the decision would be a two-body problem, right? Assuming that I'm already married or have a strong relationship in this new young time that you're giving me. Well, if we both could go abroad in the same place, in the same city, probably if I would have got a nice offer, I would have gone.
Mm-hmm.
But again,
And
it has to be a two-body decision.
No,
And for my son, I hope, for my daughter, I hope that they will come back and stay close to me. But I also know how relevant is their professional life. So it's always, I mean, life is never easy. It's a compromise. And every time we do the best choice, sometimes it's the wrong one, sometimes it's the good one.
No, I agree completely with Francesco. I mean, life is a random walk, and you never know where you end up. Hopefully not back at the starting point. That's the only point. And so I don't know what I would do now in a different condition, with a different science, in a different place, maybe. I don't know at all. And still, I will not advise. I mean, for instance, I also have my daughter. She moved away from Italy when she was 19 by herself. She went to UK, and she's still in London now, finishing her PhD. And I just told her, do what you want in your future. Of course, I would like very much to have her close to me, but that's her life. And as I said, many things that you do, I mean, when I started doing physics, I wanted to be a theorist in astrophysics, and I end up as an experimentalist in soft matter. But I'm happy about that. But it was really...
The scale is slightly smaller, yes, but
yeah, well,
still.
It has its advantages, most advantages, I would say, at the end, I discovered, because you can work on a small scale in your lab. Maybe it's more like an artisan, more than big things, but that allows you to be, I mean, in soft matter, and that since we are discussing with the group, a large, interesting group of people doing soft matter, I think that one of the good things in soft matter is that you cannot be either an experimentalist, a pure experimentalist, or a pure theorist in soft matter, because it's the kind of field where you have to be, if you're an experimentalist, you have to use as your main instrument still your brain. And if you are a theorist and you don't understand what experimentalists do, you will never do anything serious. So soft matter is good for that. But to me, it was, I came by that by chance, and many things happen in life by chance.
Okay, so that's clear. And as long as we already passed to this modern times and new generations, and both of you were heavily involved in teaching during the last 30 years. So my question is now like two-sided. The first one is, are the students of today different from the students when you started? That's the first part of the question. And are the methods that we involve in teaching different, and do they need to change? And if yes, then how? Francesco.
Well, everything is completely different. Let me be a little bit provocative and I think that if I compare my time when I was a student and present-day students at the same level, university level, but also in terms of research, one can say similar things. Now we were used to read, and now recent students are used to skim. We were used to think deeply. Students now are used to do things. In terms of research, we tried to write articles explaining things. And now we try to write articles just to write fancy writing. But, I mean, this seems to be a criticism. It's not. It's a change of way I mean, life has changed, so technology has changed the world. You have new instruments, we have new way of communicating. We have a huge amount of information to process that we didn't have at that time. So it's not a criticism, it's probably it's the right way of doing things today. But things are completely different.
Yeah. No, I agree. Things have changed, but also, I mean, it's different. Generations are different. Luckily, my generation, and which is the same generation of Francesco, of course, was a generation where more or less. Yes.
Generation-wise, I would agree, though.
Generation, yes, for sure. Well, so I would say we had, of course, an idea of a future growing. So apart from the personal position in anything, we were looking at the future as a growing thing. What I find in my children, in particular in my son, but also my daughter, is that the generations today, almost today, they are almost in the 30s now, and I mean they cannot think seriously of an open future, growing, I mean, a splendid path toward the future. And that means several things. First of all, when we were young, they told us, you have to learn these things, maybe, I don't know, spectral operators in Hilbert spaces. And we didn't know why, but we just put down our head and start doing it because that was what had to be done. My son, for instance, is different. Even if he also studied physics, then he moved to different things. But he said, why should I do things which I don't see the reason at the moment now? And I said, because you have to do it. And these, for us, was something that was planted inside. And of course, because we expect something from the future. If you cannot expect it seriously, if I were young now, I would have a hard time thinking of a splendid future for humanity and so on. If you don't have that possibility, then it's become more difficult to do things if you don't understand why. And then I think that means also spending time in reading, spending time in doing things which are boring, and that's something that I realize are important. Being bored, I think, was important in my childhood, and I like very much that all the time I was spending without doing anything, just staying there and thinking of doing something. And of course, now you cannot because of this difference in perspective.
It's also, I mean, we are somehow also forcing them to do this way, right? Because they have to process so much information that they cannot do it. I mean, this is what I like to joke by saying this is the biological way of doing physics. I mean, nowadays, we are starting, students, but also us as researchers, we are starting to accept that we don't understand something, but we know the effect of the phenomenon. And so we accept that we don't understand it, but we build on it. Right? And this is also helped by the fact that very often you find the information that you want on the web, but you don't have to really understand that information. You just want to know that it's true. No, it's a different way of not to mention the fact that even from a career point of view, we are forcing our young people to really produce a lot quickly, which is absurd. I mean, but their career, even the starting grants, all these things that we put together at European level, they really force them, or the Marie Curie, they force them to produce already at the very early stage. And so in some sense, we are forcing them to skip the deep knowledge that we try to build up in our time. Of course, we were knowledgeable in a shorter, in a smaller field. That's why I'm saying that it's not that we were better than them, it's that we are different.
Okay, super. Before I go along my line, I just saw a question on the questions and answers. I assume that the question is to both of you. And the question is there a book or article which changed your scientific life?
A book or an article which changed my scientific life. In my case, I think it's the article by Stanley and Teixeira presenting the thermodynamic of water in terms of percolation theory. That was an article which I read when I was a student, PhD student, and that had a very big impact in my life.
Well, I think it also, I had an article which is not so much because it changed but because when I started my career, I started actually with my former, a fantastic person that passed away just 2 years ago, Vittorio De Giorgio, that many of you might have known at least by name. And I was still doing my military service because I was, at my time, people still have to do something sometime in the military service. And so Vittorio gave me, I said, well, I want to see if you can do something interesting before I take you. At the time, there was not yet a PhD because I was in the first group, but just 2 years after. And he gave me a paper by Bachelor on sedimentation of particles, which still now I had problems in reading. But the story was that Vittorio wanted me to struggle on that paper, which I spent a lot of time trying to understand, and just to see what was the deep ability of thinking before taking a decision. And I still remember that paper quite well, but not because it was, well, it was actually influential, because then I did several things in sedimentation many years later, but still that was an exercise for learning what means struggling for reaching, understanding something and getting some result.
Okay, thank you very much. And I think we are basically coming to the last question, unless there are new questions that would appear there on the Q&A. And this, so I would bring you slightly back to your previous answers. So the rhythm changed, the rhythm of life changed, the requirements changed. So from in-depth search, we went to in-breadth search if you involve graph theory. So the strategy changed a lot, the strategy of living, not only in science, like basically the world is now functioning differently. And of course, you can't but notice that a lot of things got automized. And along this line, also, I already had a discussion with Francesco on that, but I would like still to hear your opinion on what is going to happen next. So the perspective. As we said, it's difficult to think about a very bright perspective for a scientist in a classical, traditional view. And this is also because of the really advances in artificial intelligence. So, and my question is not what exactly you think about artificial intelligence, because you surely think something about it. But my question would be in a slightly different twist. So you both have fundamental knowledge. And this knowledge is not like superficial, right? It's not in breadth. It's a large amount of information that you have. And you say, okay, modern students, they don't carry all this information because they can ask. So does it mean that our classical knowledge is not anymore needed when it can be replaced by Q&A with artificial intelligence? And with that, we then wrap it up. Francesco, what do you think?
I'm not going to answer exactly to your question, but let me say a few things. One is, before me, the topic was mathematics is the language of science. You need to know very well mathematics to do science. And at my age, or at least my personal life, computer appeared, and computer allowed to do science in a different way without knowing math, or actually knowing it, but not at that level. You didn't need to know how to solve a differential partial equation to do good computational work. On top of this was, to me, I always felt it as a real democratic instrument, in the sense that it was enlarging the number of scientists that could do, number of persons that could do science, thanks to the computer. Before, it was limited to the number of people that could do math properly. And now there is artificial intelligence, which is, in some sense, is very delicate, because I can see that can have the same role as the computer had for me, because they can enlarge even more. But at the same time, while the computer was an instrument that was available to essentially everybody with the personal computer development, and so in this sense was democratic, this artificial intelligence could be restricted to a minority of a person that could control it. So in this sense, I feel it also as a dangerous future. But, you know, I mean, we have to live, we have to work for making it democratic, to exploit it as much as we can. And hopefully it will be accessible to a lot of people. So I mean, I know that this is really going to change again the way of doing, or living and the way of doing science, of course. It's an instrument that I would recommend all the young people to learn, to make their own, in its own list of knowledge. They should know, all of them, how to use this type of instruments, and they should know how they are made. They should know what is the black box, in some sense, as for me was important to know what was the black box of computational physics. But I don't want to...
Roberto, and you?
Well, I also think, of course, that the new instruments that they call artificial intelligence is extremely useful for many stupid things that you can do much faster and without spending time. One of the things which is positive for sure is that it's a little bit a way of limiting the arrogance of the Anglo-Saxon speaking people, because science was something that was spoken in many languages, from German to Italian to French to Russian to English. And now we are not only asked to write practically only in English, but also in the English they think it's the English. And I do think that English is what, I mean, it should be the common language of people. So it's, and artificial intelligence allows to satisfy these people that I know, you know, not yet in physics, but in biology. Now, when you send a paper to Nature or to one of those first-class journals, they also ask you a translation which is certified in pure good English, which is ridiculous. So artificial intelligence, of course, is very useful. And after all, to me, remember, it's not intelligence, it's just the collective thinking all over the web, which is extracting what is more probable about any argument. That's artificial intelligence. I have a many discussion with my son about that. He said this also that all the ideas of humanity are just a collection of things which are around a distributed network, which are all the humanity. That might be true, but this spike of novelty, not only in science, but I would say in thinking like poetry. Try to ask to ChatGPT to write a poem. It's ridiculous for anyone that likes poetry. They are not able. They write very standard, boring, no spark of intelligence. So it's useful, as computers have been useful, as the typing machine have been useful, as everything that technology gave us will be useful to dedicate ourselves to higher level problems without having to spend time to learn, for instance, all the tables of logarithm as I did when I was a kid. Now I just take, I just take the computer, or I take Wolfram Alpha to solve an integral without thinking of solving it anymore. That's are good instruments. But at the moment, I think that creativity is still something, in terms of power, the whole humanity put together. You have to think of billions of people, not only people doing science or clever people, all people are giving a contribution to this big computer, which is there since after a long evolution of life. And for sure, it's much more creative. So it's useful, but be careful, it's not creativity.
Okay, cool. We now have a blitz. We have, within 3 minutes limit, we have 2 questions. The first question is from Frank Ritz and should be answered by 1 word, because it actually suggests the answer. Would you tell your students today to publish or perish?
Publish.
Roberto?
Publish.
Okay, and then the other question is the following. How easy do you think it would be today for a young researcher, particularly a postdoc, and having done the PhD abroad, to come back to Italy and pursue an academic career? When I look at the procedure and the number of years required, RTT, RTDA, RTDB, national qualification, it looks overwhelming. The question is from Michael Orsi.
Well, I think we can discuss this over email if there is no time, because it's a long process indeed. But the best, I mean, right now, it looks strange, but the situation is better than before. So if you are abroad, you have got some important grant, or have already a permanent position, coming back to Italy is easier than before. And we can discuss, I can suggest a way to do this.
Yes, I agree completely. At the time when me and Francesco started, it was really a random process, getting a position. After the law of 1982, where many people entered university were completely fed up, and for at least 8-9 years, no one, unless there was something very special, in my case was a person having a position that went to marry in the United States or in Libya, the position, and I've been, I got my degree 9 years before. So at that time, it was really random, and you really have to fight in getting a position. Now, of course, it's a terrible Italian things, in particular for the fact that you need to have some contacts here, and you start with nothing unless you get one of those big ERC grants or something similar. But it's, I mean, there is a path, and so it's probably better. I'm sure it's better. It's easier.
Great. It suddenly turned into a very optimistic note at the very end. So it's getting better. Regardless of the absence of bright perspective, it's getting better. So let's keep it this way. Roberto, Francesco, it was a great pleasure talking to you. I really enjoyed your answers.
Thanks.
So hopefully we repeat it soon with a bottle of wine. Thank you very much. I am sure that the audience enjoyed it as much as I did. Thank you.
Thank you, Sofia.
Thanks a lot, Francesco, Roberto, and Sofia, and thanks also to the audience for asking questions and keeping the discussion lively. So now we move on to the second part of this soft discussion, and it's my real pleasure to introduce Professor Stefano Sacanna from University of New York. Stefano did his master at the University of Bologna, followed by a PhD in physical and colloidal chemistry in Utrecht in the Netherlands, and then moved to New York, first as a research scientist, then assistant professor, associate, and then since 2022 as a full professor at the University of New York. He is also section editor in the Current Opinion in Colloids and Interfaces in Science. And Stefano can be defined as a true maestro in the field of colloidal design. And you will immediately realize that if by visiting his gallery of images on his website, where his work is showcased. He specialized in using colloidal matter to engineer nano and microstructure new material. And thanks to his work at the interface between chemistry, physics, and material science, he can design synthetic methods to create smart colloidal material. And by doing that, it does not only produce amazing material, but also gave a pivotal contribution in elucidating the mechanism of self-assembly. He studied a plethora of systems, including cell mimics, patchy particles, colloidal hexapods, which are amazing, and colloidal crystal. And today, he will talk about the colloidal crystal with this seminar entitled Crystal Clear, Enabling 3D Real Space Analysis of Ionic Colloidal Crystallization. Stefano, the floor is yours.
All right, so let me first unmute, and then I share. Oops. Can you guys see my presentation?
Yes, thank you.
Okay, good. All right. So thank you very much for the introduction. It's a great pleasure to present my work today. So I'd like to start with a very, very brief introduction because on the work we do, because well, first of all, this audience probably is already familiar with the topic, but also you know, you just gave up the perfect introduction. So my lab at New York is interested in designing and developing colloidal model systems. And what you see here, it's perhaps the most simple, the simplest colloidal model system you can think of. Those are just boring spheres. And perhaps the only remarkable thing about this system is that the particles are monodisperse, and you see you can tune the size and surface properties. But other than that, it's very standard sort of a simple system. And if you like me, you're more like a visual learner. I'm giving you just a sense for the dimension of these objects. This is one of my hair, and on top you see some of those objects we make in the lab. In this specific picture, the particles are not spherical, are cubic, and that's again to highlight the fact that we are interested in developing colloidal model system, not where we have control on size, but also shape and composition. And things can get complex, can get really complex. For example, in this next example, you see a very sophisticated colloids that consist of essentially a hollow shell with a very precise hole puncturing through. Inside, this black dots are photocatalysts that we use to generate a chemical gradient that lure in bacteria. So in the bath here, you see bacteria, in particular E. coli, and you see that when the particles are activated, the bacteria are essentially captured. And I'm showing this example not just to show you how complex those systems can get, but also because we're very much interested in what people now call active matter, which are colloidal particles that are also consuming energy, so they're driven out of the equilibrium. Now, I could tell you a lot about this, this really interesting system. Instead, I will go back to the boring case of the spheres and show you how we developed a strategy to use them as model systems for ions. So something I didn't mention before is that the reason why we design and develop colloidal model system is primarily to study self-assembly processes, and with the ultimate goal of building materials, right? And so the most natural way of assembling particles, at least intuitively, is to just combine them and let them interact with some sort of complementary interactions. And so the idea here was, what if we take a bucket of positively charged particle and one of negatively charged particles, we mix them together, should we obtain large ionic solids, or the equivalent of ionic solids, where the particles assemble into a well-defined lattice? And then by changing the size ratio of these particles, can we get access to all sort of different crystalline structures? And well, if you have done any, if you have any experience in colloidal systems, especially in water, you know that if you simply mix oppositely charged, you will obtain a giant mass. The particles will just aggregate and form aggregates rather than crystals. So here you see in the video what you will get. And the reason is that if there is nothing to prevent the particles to make physical contact, or to come into physical contact, the particles will experience strong van der Waals forces that will bind the particles irreversibly. And irreversible interaction is not good news for self-assembly. You need instead some soft type of interaction potential where particles have the opportunity to correct defect, anneal, and reconfigure. And so the approach we took, and by we, I mean my students, Ted, was to sort of tame that strong interaction using what we call molecular spacers. And I'm going to use an analogy here with strong, if you take strong magnetic beads, this neodymium magnet, and you let them interact, they will bind very strongly. And sometimes you have a hard time to take them apart. But if you build a non-magnetic shell around it, you can tame down that interaction, and then obtain some soft reconfigurable interaction. So at the colloidal level, we do something similar. We have three main ingredients. We have what we call the attractor, that are not not magnetic particles, but are charged particles. So we typically use polystyrene. But what I'm going to say applies to pretty much any colloidal system that has a charge. And so we choose here polystyrene because they're experimentally very easy to make, and they're almost density matched with water. But you will see later on in the project, in my talk, I will also show you other systems. But the idea is that we have the attractors, so two oppositely charged building blocks. You have an attenuator, which in the case of a colloidal system consists of a well-defined polymer brush. Some sort of a non-charged spacer that's fixed the distance between the particles. And then the third and last ingredient is simply salt. And the salt here is used to screen the to adjust the bi-screening length. With this three ingredient, you can cook up a simple model that combines essentially the LBO and Alexander Dejean model for polymer repulsion. You get this pair potential, and the only things I want you to pay attention is that this minima here, this attractive minima, it's function, you can tune it using salt concentration. So the bi-screening length, which is in turn you can experimentally control with salt concentration in the system. And I want to stress this fact because as an experimentalist, this is something very easy to change. So you can easily control the salt interaction, the salt concentration with precision. And a more pictorial way of thinking about this picture is a competition, it's a competition between steric repulsion that's sort of given by the polymer brush and the electrostatic attraction. And the length scale, it's set by the bi-screening length. So when the bi-screening length is shorter than the brush, particles do not interact. When it's longer than the brush, the particles start to interact. And so experimentally, what you see is that if you work at low salt concentration, so in this regime here, you have strong attraction. particles just aggregate and flocculate as you would expect. If you work at a very high salt concentration, when the device cleaning length is it's very short compared to the brush, you have a stable suspension. And in between, there is that sweet spot where the interaction is just right to form crystals, ionic crystals. And it's easy to spot experimentally because that's the regime where you start see opalescence, an indication that you have a crystal. Now, there is another, so you see, experimentally it's very easy to tune the system, but experimentally there's another things you can do that usually is hard, and here it turns out to be very simple, which is fixing the crystal. In self-assembly, assembling it's one issue, fixing whatever you have assembled is another, because these microstructures are held together by very weak forces. So if you later want to manipulate whatever you have created, you have to figure out how to fix it. And here, fixing the structures is as simple as diluting with pure solvent, reducing the salt concentration. Because as you reduce the salt concentration, the interaction increases until at some point the polymer brush fails, the particles sort of make contact, and Van der Waals does the rest, fix the crystal. So then this delicate crystal can be tweezed out as a monolith and crack it open, and then with SEM you can study the internal structures. So here see two examples. These two materials are clearly polycrystalline, but you see that there are two different crystal structures, and that's because the size ratio between building blocks have been changed. So here you have a cesium chloride type of structure, and here you have some other structure which I don't remember right now. You can do something even more interesting, which is instead of doing this experiment in bulk, like in large container, and getting this polycrystalline phases, you can actually grow the crystals in situ. So and actually look at them as they grow. You see here the same experiment done in a more controlled way under the microscope, where you see again the equivalent of cesium chloride crystal nucleating and growing out of this sample. And again, you can fix them and then perform SEM, and you can change the size ratio, and you can demonstrate that you can form all sorts of different crystal structures. The one I didn't remember before was CS60. And these are all crystalline structures that people have assembled previously using DNA-coded particles, which it's obviously a more involved method to do. To assemble particles, because it's hard to do it in large scale. Whereas here is charge comes for free, and so when the crystals can grow large enough to actually see them by naked eye and show beautiful coloration, and in order to study the structures for simple crystalline structures like cesium chloride or sodium chloride, it's simple enough that you can take a few of these flakes, these crystals, do SEM, and then you can just look at the surface and you can recognize simple crystalline planes. Also, if you know the size ratio between positive and negative, that can help you. But you will see this is a sticky point, because as the crystals becomes more complex, just looking at the external habit and the external faces, it's not as informative, or rather, I should say, it's not easy to determine the exact crystal structures by just looking at the external of the crystal. So what you'll show you next in the paper is a methodology that or a system that allows to do a full in-depth characterization of these crystals. But before I dived into that, I want to show you some of these more complex crystals and how we discover them. So up until this what I said till now, the potential between the particles is fixed. So we test the different salt concentration, then we pick the one that shows formation of colors, and the system is sealed, so the concentration doesn't change. But you can perform these crystallization experiments in a setup where you essentially constantly dilute the salt. And remember, the salt concentration affected the bioscreening length that in turn changes the bond energy between the particles. So here you have a COMSOL simulation of what happened in this capillary that you see here. So the capillary is immersed in a reservoir bath, and you open one side, and you start with high concentration of salt inside the capillary. And as the salt concentration diffuses out, you see that the salt concentration in the capillary changes in time and space. And so the idea is that now with one single experiment, you can probe many, many different experimental conditions, or many different ways in which the bond interaction changes, and then look whether this is an effect on the crystals. Just to convince you that this actually works, here is an example where this is the initial starting point when you have high salt concentration. Particles do not interact attractively, so they're just repulsive. So you have a stable gas. When we open one end, salt goes away, diffuses out this way. So the salt concentration decreases first in this region, and then you have a front that moves towards the left. And so the expectation is that should also be the way crystals, the crystallization front moves. And indeed, if you look at this video, you'll see that the crystals start from the right, and then you have this crystallization front that move towards the left. So that sort of gives some confidence that indeed the system is very responsive to salt concentration, and by controlling this gradient, you also can control the exact spot where the nucleation occurs. Then what we can do is to, again, based on this COMSOL simulation, knowing the geometry of the capillary and the concentration, we can build a map of where you have time here in the y-axis. The x-axis essentially is the distance from the opening in the capillary. So 0 would be the open end, say this one. And now you see that in each position in the capillary, as the time goes by, you have a different the interaction energy between particles changes with follows. You have different gradients in close to the open end. You go from non-interactive to strong interaction really fast. But if you go, say, close to the this region here, the closed end, you see the interaction change more slowly. You have less steep gradients. And that, so in this red area here, when interaction is like above 20 kBT, say, crystals are fixed. Below 7 is just approximate numbers. You have stable, and this yellow area is the interesting area where the particles start to crystallize. So close to the open end, you have a lot of very small small crystals with a lot of defects. Then you have a region where you have good crystals, and you have region where we observe hopper-like growth, where crystals grows with non-well-defined habits. And then there is regions where you obtain large crystals, you also get polymorphs or different structures. And remember, this is the same system, the same capillary. The only things we're changing is the time dependence of the interactions. For example, let me give you an example of hopper growth. So when in the region where the crystal grow following this hopper-like growth, you start with well-defined habits, but then you see that as the interaction ramps up, corners and edges grow faster, and then you get this characteristic hopper look that reminds of in the atomic world. The bismuth, for example, is a classic example of hopper crystal, where corner and edges grow faster. And here you have a kind of comparison between a closed system that is tuned to actually give you perfect crystals, and an open system where the interaction constantly increases, and you get this hopper-like behavior that turns into in the most extreme cases. In the most extreme cases, you get even dendritic growth. And again, this is the same sample. Perhaps the most interesting observation, though, is the fact that together with the cesium chloride crystals that you suspect, you also find alternative, I shouldn't call it polymorph really, because we turned out that, for example, this one here is a thorium phosphide-like crystal, colloidal crystals, is actually not a polymorph, it's a different, simply a different crystal structure. This forms in a different region in the capillary. And there is also another example here of something we just finished to characterize, or kind of. This seems to be like a new new crystal structure. We couldn't really find an analog. And it's like very open, and it tends to grow anisotropically and form this, sometimes forms this like crazy network or like spider-looking crystals. Let me just zoom in into this one because it's really interesting. And again, same exact building blocks. So these are the same particles that in principle should just give you cesium chloride-like structures. So this is like also a single crystal. So if you change illumination, you get, you know, a nice reflection. And we capture how it grows, which is also very interesting. And we are now studying this. Initially, we thought it was like because of impurities, but it turns out that is actually, you know, we thought that there was an impurity in the center that caused this, but it's reproducible. It's actually pretty solid. So it's a real crystal. So this is where we introduced this new system that allows us to characterize those crystals more in details, because now this is an example where just by looking at optical microscopy or SEM images, you can't really quite understand what's going on. Ideally, you would like to follow the dynamics, and you would like to know have a full three-dimensional imaging that will give you a lot more information to understand this crystals. And of course, the first things you can do is to fluorescently label your particles, so at least you know who is positive and who is negative. And that's already gives you some extra information. Like, for example, you can tell which crystal plane grows or nucleates preferentially on the substrate. And for example, a simple observation is that if you have a negatively charged substrate, crystals preferentially grow from the 1,0,0 phase that has the highest positively charged density, and that's you can also tell this by just looking at the color of crystals. So since each crystal is nucleated on the substrate, you know, has a different face looking at you, the color of this crystal changes, is slightly different. And you see that the majority of crystals when you have a negatively charged substrate is this orange-looking crystals, which is the one that sort of forms this pyramid, because forms from the 1,0,0 phase. And you can also double check, you know, by artificially increasing the charge of the substrate, you can prove that, you know, you can show that pretty much all crystals actually grow in that fashion and form these pyramids. But this is not, you know, this already helps, but you know, as soon as you move into the bulk of the crystals, you lose signal very fast, and that's because again, the particles are not, in this case, are polystyrene, so they're not refractive index matched, and so you can't really perform 3D scans. And so here is where we introduce this a system of optically transparent water particles. This is something. This is actually a system that I learned of its existence during my PhD from one of the work of one paper from Roberto Piazza. And the idea is to use this polymer, this fluorinated polymer, and make positive and negatively charged particles, and then combine them using the same type of interactions, polymer, same electrostatic interaction mediated by this polymer spacers, assemble into crystals, then perform 3D scanning, and then that would allow to extract the full 3D coordinates of the crystal. And then you can do all sort of internal analysis by sectioning the crystal, or even calculate diffraction pattern. That should give you a much better tool to study these crystallization processes. I'm going to skim through these chemistry of how we assemble or how we created these fluorinated particles, because it's quite frankly boring. It's just I just want to mention that even though these particles exist in the negative form, making them positively charged is actually quite difficult. And so large part of this slide was devoted to explain how we make them positive. But I guess I can talk offline if you're interested. Instead, I just want to show you the result. These are the particles I'm talking about. They have a refractive index of 1.38. They're fairly monodisperse. And when you add in when you add a little bit of DMSO to your system, you can perfectly match them, and they are transparent now. So when you perform crystallization, what you will see, or what I should say, what you should not see, is the crystals, because they're transparent. So if you actually look carefully, you will see something that looks like ice crystals. But if you shine light, then oops. If you shine light, actually you see that those are like nice single crystals. But they are fully transparent, optically transparent, so you can do confocal microscopy now, not just the first layer, but you can actually image the whole crystal. This is a sort of a comparison between what we used to do with polystyrene. So it's a volumetric scan. If you take a volumetric scan, already at a few micron deep into the crystals, it's the pitch dark. There's no light going through, and you can't recognize particles. But in this fluorinated system, you can scan deep into the bulk, over 90 micron deep. And so a typical workflow consists on assembling the crystal out of the fluorinated particles, perform a volumetric scan, and then in this volume that you've scanned, you identify the crystalline region. Let me just play the movie. Then you extract the coordinate. So this is a simple 3D coordinate tracking, and then use those coordinates to build, simple, Blender model that you can use to, you can slice it and collect all the different planes. And so if you have a crystal that is more complex than a cesium chloride, that helps a lot to be able to section the crystals along different crystalline planes. For example, this one is copper gold, and by looking at all different, you can look at all different planes and then match with what you find in the literature. You can also take the coordinates and conform them to a candidate crystal. So if you suspect that you have a certain crystals, you can take the coordinate from the experiment, from the 3D extraction, conform it to the target crystal, and then calculate. You can feed this to software that can compute the diffraction pattern, and then compare it to the the real, the diffraction pattern of the real crystal. And so here you have a comparison of like the actual real crystal and the diffraction pattern of the crystals that we prepare in experiment up here. And we also, I won't talk about simulation in this talk, but you can also do simulations, and that's it's still there's still a little bit of labor involved. You have to it's kind of a trial and error, but this process can be automated, and it gives a great help when it's about identifying new crystals. The last things I want to show you in the few minutes I have left is another. This is, and what I'm going to show you now is kind of work in progress. So I just want to give you a flavor for where we're heading. It's studying in more details defects. For example, if you're not familiar, if you're familiar with crystals, molecular atomic crystals, you can immediately tell that this is an example, textbook example of twinning, where you have these two crystals, they grow and sharing a plane, essentially forming a twin. But you can actually perform a 3D reconstruction, well, first of all, you can just scan the crystals and look at vacancies and other type of defects, but you can get a better idea on how this habit came along, and you realize that if you do that, you realize that the crystals has a twin plane. You can actually check what twin plane is. In this case, a 1-1 plane. So this habit is the result of two crystals that are joined, if you want, or they share 1-1 plane, and so then you have this 1-1-1-0 plane that you run across the two. So in other words, if you look at this model here, that's how this crystal. And this is still pretty easy to understand even without these tools. But then there are more complicated examples. For example, often you see a cube that have other cubes protruding out, and you might wonder, what's going on here. And if you do the same type of analysis, it's actually pretty easy to figure out what's going on. Here you have not one but two twin planes that are parallel to each other, and so now you have three cubes that are sharing the 1-1 plane. And similarly, here you have often you find this characteristic V shape, and this is a case where you have also two twin planes, but now they're not parallel to each other. Instead, they form this 70 degrees angle, which sort of reflect this V shape or the angle that you see in the macroscopic habit. And finally, something again is work in progress, but it's very promising, is to look at the dynamics of these defects, not just the formation, but also, for example, how the simplest things you can look at single vacancies. How do they, do they move or not? And so you can take again real crystals like that, identify all the defects inside. So here is a crystal that has a lot of defects. The green dots are vacancies of positive charged particles, and the yellow vacancies of negative charged particles. You have impurities. Then what you can do is to isolate one plane where you have two isolated vacancies, and this plane is sandwiched between two perfect planes, and then just look at the dynamics. And you see that the vacancies actually are remarkably immobile. They don't move. We can even melt the crystals by changing the salt concentration, and you will see that through the melting, the two vacancies will not move. In fact, the melting occurs via, it almost seems like a sublimation rather than the melting. You see that this part now start melting or evaporating, and the crystals dissolve. Okay, I heard a beep, so I guess my time it's over. So I'll end up with the outlook, something that is either in the process of being done or it's preliminary. One is to use, so up until now we use spherical particles to mimic ionic crystals, because ions are spherical, but we work with colloids, so we're not limited to spherical particles. We can perhaps for example, use ellipsoids or rods. That would be very interesting. That's actually easy to do because you can take the same building blocks and stretch them into rods, or you can do something more complicated where you have now a mix of spherical and non-spherical building blocks, or even like not a binary system. You can have a three-particle system or more, and of course everyone's favorite these days are patchy particles that up until now people assemble again with using DNA. But I'm a strong supporter of electrostatic interactions. It's much simpler and cheap. So these are some of the direction we are going. And the very, very last slide is the most important one, is the acknowledgement to who did all the work. And in my lab, these are the experimentalists that are doing all the hard work. And then we have simulation support from the hockey group and funding from the US Army. And so with this, I'd like to end my talk, and thank you for listening to me, and happy to take questions.
Thanks a lot, Stefano. And now the floor is open for questions. So we have the first one from Francesco.
Mute. Okay, can you hear me?
Yes.
Okay. Beautiful talk, Stefano, as usual. So just
Thank you.
talk about your. I mean, it's great that you can really, in a simple way, do these crystals, all these different type of crystal, and you study all this process. Going back to your last slide, you said that now you are going in the direction of creating patchy particles based on charges, right?
Yeah.
Are you thinking about the possibility of doing the colloidal water with the 2 positive charges to negative on the paper?
When you start talking, I knew where you were going. Yes. It's now I see that. I mean, I remember we talked about it a long time ago, and I was a little bit skeptic, not because of the water idea, but it was because of the actual DNA interactions. And now that we have this much simpler system, I really think it's that project would be more experimentally more accessible.
So let's do it.
Sure. Yeah.
Okay.
Yeah, we're actually, working. I mean, I'm working with Pine for obviously to make the diamond, and once that works, then I guess that's pretty much a matter of mixing the particles then.
Thank you. So if the participants have questions, please raise your hand, and then you will be able to ask it directly. In the meanwhile, I have also a question. What is your time resolution when you look at the defect dynamics? You've shown us the beautiful video, but probably I missed the time scale. This is the first one. And then the second one is how important it is in your process to control the temperature, not to induce defects or have a proper crystallization.
Yeah. So I don't have a precise answer about the time resolution, because that depends on 2 things. One is how fast your confocal scanner. So one is money. We have a fairly recent but confocal, but certainly not the top of the line. So and the second parameter is the size of the particles, right? So the particles I've shown so far, they are in the order. So if you want to do full 3D characterization, you need at least 400 nanometer. Otherwise, it's very hard to do particle tracking. So that I think would set the time scale for how fast they move, but also depends what kind of. So if you want to look at bulk defect in a large crystals, it also depends on how big is the crystal. So how much planes you want to scan. In the video that I've shown you, we actually do a full scan, then we identify a plane, then we focus on that plane, and then you can scan really fast in just a single plane. So that video, again, I don't know on top of my head what was the. I believe is a roughly real time. But we can certainly scan faster. It's just the particles don't even move that fast. So the limits, just to summarize, the limits is how big of a volume you want to scan, how fast your microscope goes, and the size of the particles that is limited to 400 nanometer if you want to do 3D.
Thank you. Stefano Buzzacaro has a question for you.
Hi, Stefano, as I say in
Hi.
and Stefano.
Yes.
Amazing talk. I have two questions. The first one, when you move from a polystyrene particle to fluorinated particle, I think that gravity start to play a role. Did you see some difference in the crystal formation when gravity start to play a role? Because the density of fluorinated particle is much larger than polystyrene particle.
Yes, you're absolutely right. This is also a limitation. What I can say is that if you stay on the 400 nanometer sort of regime, you can still grow fairly three-dimensional crystals. That they don't grow as big as the polystyrene when they're perfectly density matched. If you use much larger particles, like above half a micron or so, then limitations start to get really severe, a problem. In terms of differences, it's still kind of preliminary. We've done quite a bit of experiments, but I can't, from what I've seen so far, I didn't see a different, for example, you use polystyrene and you get cesium chloride, and you fluorinate and you get different structures. That I haven't seen. So that is pretty consistent so far. But I do see that the crystals grow with less defined habits, and of course they're sort of affected by this limitation.
Okay. And if I have time, I have another question for you. It seems that you are using pluronic as a polymeric spicer. Is it correct?
We actually use a whole bunch of different. It turns out that it seems that Pluron is always the best for whatever reason. But for example, we also, instead of changing the device screening length, we kept the device screening length and changed the length of the spacer. So we went from F108, F127, 68, and so on. And you get the same type of results. We also use, oh boy, I forgot, a different surfactant, just to show that as long as you have a well-defined brush that is uncharged, you will get the same results.
My question is related to the fact that because you have this PEG unit, the fact if you change the salt, I don't know, I think you use sodium chloride, the length of the pluronic spacer could change, and what is more interesting, could change with temperature.
Yes, absolutely, no doubt. I mean, it's basically what you see is a shift at which the shift in concentration where that crystallization occurs. Definitely a temperature, and I haven't changed the type of salt. We'll always use sodium chloride, but I can totally see this happening too. Yeah.
Okay. Thank you.
Thank you. We have another question from Achille Giacometti.
Yes, thank you. Thank you, Stefano. Terrific talk. Thank you very much. I have a question related to an old predictions by Wigner, who nearly 100 years ago predicted that you can have a crystals purely stabilized by Coulomb repulsion interaction. So of course, this is a crystal at a very low density. Have you ever considered this possibility? Because essentially you can do this with the things that you have on hand already.
Yeah. So that would require repulsion. So just one type of particle, say all negative, say, and then they're repulsive, right?
Right.
The problem here, in order to get a Wigner crystal, is that the interaction are very short range here compared to the size of the particles, because we are in water, right? So the bi-screening length is always short.
Oh,
but
yes.
we do get Wigner crystal in say if we get the particles into THF, or like you will need a longer. You are at a lower dielectric constant.
Yes.
So,
okay. Yes, I agree. Yeah. Okay. Thank you.
Yeah.
Okay, so Achille, do you have another question? Because I see again the raised hand.
No, sorry, I was trying to lower my hand. Sorry.
Okay. Thank you. So is there any last question for Stefano? Okay, if this is not the case, I would take again the opportunity to thank him for the great talk and the discussion after. It has been a real pleasure having you here today. And before closing, I would like to remind two things. First one is the registration for the IsoDays is now open, so you can just go on the website and register. We are looking really forward to see you in Florence this year. And then regarding the soft discussions, we have the next date, March 26th, and we will have Professor Kathleen Steve from the University of Pennsylvania for the Ask Me Anything, followed by a talk by Professor Lideric Bouquet from École Normale Supérieure. And I'm sure it will be another amazing event as today. And with that, I would like to thank again all the speakers, Roberto Piazza, Sciortino, Sofia, and Stefano, and wish you a good evening. Bye.
Bye-bye.